Nerd alert!
This video is intended for informational purposes only. Do not attempt to show off any of this knowledge to your close family, friends, or enemies without precaution. First ensure that your family member, friend, or enemy is a nerd just like you. Otherwise, you will risk them losing interest within 10 seconds and leaving you. Viewer discretion is advised.
So I recently graduated from my bachelor's in aerospace engineering at TU Delft, and I'm currently suffering through my final year of the space engineering master's program. It's great to see how much I've learned in these few years, but every time I talk with other people, I realize how much I've lost touch with reality.
Wait, so what exactly do you do?
Well, I work with Airbus on the thermal control of spacecraft, because obviously there's no air in space, so you only get conductive heat flow. That's especially an issue when you're in a sun-synchronous orbit, having long eclipses and then suddenly a peak solar flux, resulting in negative values for your heat control loop. So if you space materials to absorb the heat in the form of heat.
Huh?
Yeah, that never happened. So anyway, to prevent this from happening, I'm going to talk to you about more interesting matters, namely your questions about spaceflight. Do aliens exist? And how do we look for them? The first thing is to find a planet outside of our solar system, which is called an exoplanet. In order for there to be life on this planet, we believe that there should be liquid water present, because all life on Earth is also based on liquid water. Such a planet is orbiting a star, and it should not be too close to the star, because it would be too hot for liquid water to be present. It should also not be too far away, because there could only be ice. Somewhere in the middle lies the habitable zone, where liquid water could exist. The issue with actually finding exoplanets is that they are much smaller than the star which they are orbiting, and they are also much less bright. But lucky for us, there are some really clever methods to detect exoplanets anyway. Method 1. The transit method. When we are observing a star, it usually has a constant brightness throughout time. When there is a planet orbiting the star, and it comes in between the star and us, it blocks some of the light that comes from the star towards us. We then see a dimmer star. This image is an example of what the brightness of a star would look like throughout time. You can see that it dips somewhere in the middle, and this means that the planet is in front of it. A bit later, the brightness goes back up again, which means that the planet is not in between the star and us anymore. This pattern repeats every time that the planet has completed one orbit around its star. So if you ever happen to be staring at a star and you see it suddenly get less bright, this could mean that there is indeed a cloud above you. Yeah, sorry guys, the transit method is far too weak to see with your own eyes. Method 2. The radial velocity method, or also known as the Doppler method. When a planet is orbiting a star, the star's gravity pulls the planet towards itself, which is why the planet orbits in circles around the star. But at the same time, the planet's gravity also pulls the star towards itself. Both of these forces are equally large, but because the star is much heavier than the planet, its acceleration is also much smaller. We know this from Newton's second law. Force is mass times acceleration. The star has a large mass, hence a small acceleration. Regardless, the star still moves by a tiny bit, which we can measure. But how do we measure this tiny movement? This is where the Doppler effect comes into play. The Doppler effect essentially means that waves are compressed when the source and observer move towards each other, and the waves are stretched when the source and observer move away from each other. This works with all types of waves, so not only sound, but also with light. When the star moves towards us, the waves are compressed and become more blue, which is called blue shift. When the star moves away, the waves become more red, which is called redshift. Alright, that was a rather lengthy explanation, but it essentially means this. If you look at a star and it becomes a bit more blue, then a bit more red, a bit more blue, a bit more red, it means that it is likely that a planet is orbiting the star. And the movement of this planet results in the star moving in circles as well. And that is what you see with these Doppler shifts. So if you ever happen to be staring at a star and you see it become more blue, then more red, more blue, more red, this could mean that you're getting arrested. Once again, sorry, also the Doppler method is too weak to see with your own eyes. Do the thousands of satellites that are orbiting Earth have an impact on astronomy? You may have heard about the Starlink satellites from the genius yet crazy CEO of SpaceX, Elon Musk. Over 5,000 of these satellites are currently orbiting Earth, and some astronomers have already complained about them. One problem with launching this many satellites is the risk of creating space debris. These are pieces of junk flying through space uncontrollably. This is a complex topic which would deserve its own video. The problem which I will talk about now is that the Starlink satellites are very reflective, so they become bright when the sun shines on them. This results in interesting looking light streaks when you take pictures, but astronomers don't like them because they obstruct the view. Elon's solution for this was to paint the satellites black. It is impossible to make the satellites completely invisible, but this is a good enough solution for the light streak problem. Now you may wonder, even if the satellite is completely black, it will still block all the stars behind it. Doesn't that ruin the pictures too? Well, not really. Okay, I won't leave you hanging like that. So the question was, why is it not really a problem when a satellite flies in front of a star while we're taking a picture? When you take a picture, the light from outside reaches the sensor of your camera. The longer you expose this sensor to light, the brighter the image will be. So when it is really dark, like the night sky, it can take many minutes or even hours to take a single picture. I have a simple example here which you can also try at home. This is a picture I took in daylight, and the sensor was exposed for about 0.02 seconds. I can take the exact same picture, but instead of exposing the sensor for only 0.02 seconds, I expose it for an entire 10 seconds. And because of all that light, the image will look like this. Taking the same two pictures at night results in this. Where the 10-second exposure was much too bright for daylight, it actually suits the nighttime conditions. On the other hand, the very short exposure is very good for daylight conditions, but it's not enough for nighttime. In short, most pictures that astronomers take have very long exposure times. But how is this related to satellites obstructing the view? This is where the interesting thing happens, and this is also something which you can try at home. I will again take a 10-second picture in the dark, but now I will move my hand across the view like this. You probably expect the hand to be visible in the final picture because you clearly moved it in front of the camera. But actually, the result is this. So, where's my hand? I will explain it in the following way. The camera is pointing at the plant in this case, which is completely stationary. So the light that comes from the plant will be the exact same for all those 10 seconds. On the contrary, my hand is only moving in the picture for a fraction of that time, so the light that the camera receives from my hand is very dim. As a result, the plant gives off much more light than my hand does, and therefore you will see mostly the plant in the picture. You can play with this a bit more. Instead of moving my hand quickly in front of the camera, I can also keep it there for a while. So let's say that for 5 of those 10 seconds of exposure, my hand is in the picture, and for the other 5 seconds, my hand is not in the picture. The result looks like this. If you think about it with the same explanation which I told you before, it makes sense, because about 50% of the time the camera sees my hand, while the other 50% of the time my camera sees the plant, so the final image becomes a mix of the two. The exact same holds for a satellite moving in front of a star. Most of the time the camera will see light from the star, and only a very short amount of time will the camera see light from the satellite. Therefore, the satellite doesn't really obstruct the view. You can also see why this doesn't really work out when the satellite is really bright, like the Starlink satellites were. In that case, the satellite is way brighter than the star, and the star won't really be able to cancel out the light from the satellite. Why does the James Webb Space Telescope look like this? Well, the full story is incredibly complicated, and there are many interesting videos about it, such as this video from Smarter Every Day. I highly recommend taking a look at it. For now, I will just talk about the most prominent features. Probably the first thing that you see is the primary mirror, which is made up out of 18 individual smaller mirrors. These small mirrors are much easier to manufacture than a single large mirror, and are also much less heavy. The small mirrors have hexagonal shapes because you can pack those much more closely together than circles. You can see in this example that the hexagons completely fill up the space, while the circles leave some empty space in between. I guess this does indeed prove that the hexagon is the bestagon. Oh, thank you, thank you. You're too kind. So the next important thing to know about this mirror is that it does not actually take pictures of visible light, but only of infrared radiation. This is why the mirrors are coated with an extremely thin gold layer, because gold reflects infrared radiation very well. Gold is not a good reflector of visible light, so that is why visible light telescopes such as Hubble use aluminium coatings instead. Now you might think us humans cannot see infrared radiation, so how can we see any of the images that Webb has made, because those are only in infrared? Well, because the images are given false colors. To us, there is no difference between infrared with a wavelength of, for example, 1 micrometer or 2 micrometers, because we cannot see them anyway. But what we can do is that we can take these wavelengths and shift them to the visible spectrum. So, for example, if we show the 1 micrometer waves as the color blue and the 2 micrometer waves as red, we can see what the image roughly looks like if it were in the visible spectrum. So even though technically the colors we see in this image are fake, they still are a good representation of what it looks like in reality. One extra challenge that is associated with taking infrared pictures is that infrared radiation is emitted by every single object that has a non-zero temperature. And by non-zero I mean above 0 Kelvin, which is literally every object. So to prevent stray radiative heat from the sun and also the spacecraft itself from showing up in the pictures, a huge heat shield is placed behind the mirror. This blocks direct sunlight and also keeps the mirrors themselves cold, because the colder an object, the less infrared radiation it emits. So if we keep the mirror cold, we can ensure that the infrared radiation from itself does not show up in the pictures. This ensures that the images only show the faraway objects which we want to see. Well, I'm really sad to inform you, but it's already the end of the video. I hope you learned something. I'm sorry that it has only been 3 questions, but I really felt like it was interesting to go a bit more into detail because I know you guys are smart and you can handle that stuff. Now, do be careful about the level of detail that you go in with your family, friends or enemies, because otherwise you'll end up like the stupid guy from the beginning of the video, which definitely wasn't me. Anyway, now you know what to say. Come on, you can do it.
Wait, so what exactly do you do?
I mean, the details of it are not too interesting, but did you actually know that it's possible to detect planets far away from our solar system just by looking at another star?
Wait, really? How do you know all that stuff?
I have my sources.